Well, my next example should remind you of something we did in Calculus 1. This example shows how to find something called a partial derivative, think derivative, by using the definition. Do you remember the definition of derivative in Calculus 1? Limit as delta x approaches 0 of f of x plus delta x minus f of x, all that over delta x.
Oh yeah?
Oh yeah. I hope you remember that.
Oh yeah?
Yeah, I do hope you remember that.
Oh yeah.
Oh, I'm glad you do. Okay, so here we go. For this function, f of xy equals x squared plus y squared, find each of the limits. Now look at this. Limit delta x goes to 0, f of x plus delta xy minus f of xy over delta x. Doesn't that look familiar? You take out this y here because it's a function of two variables, and that would be the same as the definition of derivative of f of x. As it turns out, it's the definition of the partial derivative. And same story with this one. I think you could see f of x, y plus delta y minus f of xy over delta y as delta y approaches 0. That's called the partial derivative with respect to y. So how do you do that with this particular function? We'd put x plus delta x in for x and square it. We'd put y in for y and square that. I guess we were doing that anyway. So this part is f of delta x plus delta xy. And this is just f of xy, the function itself. There it is, see, right there. So what does that give us? Well, I think you can see this is x squared plus 2x delta x plus delta x squared plus y squared, then minus x squared minus y squared. So what doesn't cancel out is the 2x delta x and the delta x squared. And that's all over delta x. If you factored out this delta x and canceled it, you'd have 2x plus delta x as delta x approaches 0. Well, as delta x approaches 0, it's just 2x. And so what we found was the partial derivative of this function with respect to x is 2x. And I'm not going to do it, but you should see for yourself that the derivative, the partial derivative with respect to y, just based on this, comes out as 2y. So I'll leave that for you to do on your own.
Okay.
Okay, that's good. So all the properties of limits are still valid for functions of multiple variables, and we also have the following theorem, and that's the continuity of a composite function. If h is continuous at the point x of 0, y sub 0, and g is continuous at h of x sub 0, y sub 0, and the composite function g of h of x sub 0, y sub 0 is also continuous at x sub 0, y sub 0. I think we may have even had a similar theorem in Calc 1. So notice the function g, the way g is written, is a function of a single variable, or could be. So, discuss the continuity of the composite function f composed with g. F of t is 1 over t, and g of xy is x squared plus y squared. Whoa. So what would that mean? F composed with g. So we want f of g of xy. That would be 1 over x squared plus y squared. So that's not continuous, where we have denominator equal to 0. But other than that, it's okay. So really, it's just the graph of 1 over x squared plus y squared. And again, I had to cheat on this one. I had to take the x squared plus y squared and add a small number to it, because it would say 0, 0 is not in the domain. It wouldn't draw it for me, so I tricked it into drawing the graph, and that's kind of what it looks like. It looks like a big hollow bump. Of course, it keeps going up forever, but that is our graph of this composite function. So I hope that's okay. I hope everyone understands.
Okay.
Very good.